Okay, moving on to question 5. We have two particles connected by a light inextensible string. They pass over a smooth pulley. Important, smooth pulley just means there will be no loss due to friction. The system is released from rest. Both particles are 0.5 meters above the horizontal. And in the subsequent motion, the 2 kilogram or the 0.2 kilogram particle does not touch the pulley. In other words, the pulley is far enough away that it doesn't get affected by the pulley system. And the first thing they want us to do is show that the magnitude of the acceleration of the particles is 6 meters per second, and they want us to find the tension in the string. Okay, so we need to update our diagram and put in some key information to help us solve the problem. So the first thing we're going to do is look at the two particles and consider in which direction they're going. Now, if you look at the weight of the two particles, the 8 kilogram or the 0.8 kilogram particle is heavier. So its direction of motion is going to be in this direction. And we'll just label it as such. And the 0.2 kilogram particle, its direction of motion will be in this direction. Now, that's important because when we consider these particles and we want to find acceleration and the tension between them, we need to use Newton's second law. And Newton's second law is then the resultant force. So we want to work out which are the positive forces and which are the negative forces. Now, usually if this was in a straight line, we wouldn't have to worry. But because these are moving in opposite directions, it's important that we label the equation or the two particles as such. Okay, now what we're going to do is we're going to consider any forces acting on the particle. So the only force acting on this particle that is given to us that we know is the 8 newtons due to weight. So weight is just mass times the gravitational constant. We're using 10, so we will get 8 newtons. Okay, and same for the 0.2 kilogram particle, it will have 2 newtons of weight. Okay. The other forces that are not labeled or not given to us, which we're going to have to find, there is some tension force acting on both the particles. And since this is a one inextensible string, those two tensions must be the same. And that's what we're going to use to solve the rest of our equations. So, using Newton's second law of force equals mass times acceleration, we're going to look at the two components separately. Okay? Because they're moving in two different directions, we can't consider the net force as a whole system because the particles are not moving in the same direction. So we'll look at each component separately. So if we look at the 0.8 kilogram particle, the 8 newtons is going in the direction of motion, and the tension is going in the opposite direction. So we're going to subtract it. And this must be equal to its mass. Its mass is 0.8, and its acceleration is a, because we don't know it yet. Okay, we're just going to solve for t. So we're going to make t the subject of the formula, and you'll see why we need that later on. So I'm going to move the t over to this side and the 0.8 over to that side. That's going to give me t equal to 8 minus 0.8a. So there we have the first particle. Now we can do the same thing for the second particle, remembering that the direction of motion is now different. So in the 0.2 particle, the tension is the thing moving in the direction of motion. It's providing the pulling force, and the weight force is going in the opposite direction. And this is the mass of 0.2a. So now you can see why I wanted to solve for t. I could make t the subject of the formula, and then we can solve for a. So this will just be 0.2a plus 2. So there I have my two equations. And the way we've written these out, you can see we have t equal to something and t equal to something. T is equal to both of those things. That must mean that they must be equal to each other. And so we have 8 equal to 0.8a equal to 0.2a plus 2. You can see if I take the 0.8a over to the other side, I'm going to get 1a over here, and I'm going to get 6. And so we can say the acceleration is equal to 6 meters per second as required. Right, all we need to do now is find the tension in the string, and from the highlighted green part, you can see we have two equations that we can use. So you can use either one. So I'll use the second one. So I'll say that t is equal to 0.2a plus 2. We know that a is equal to 6. T is equal to 0.2 times 6 plus 2. That's going to give me 1.2 plus 2, which is 3.2 newtons. Right, moving on to part B. When the 0.8 kilogram particle reaches the floor, it comes to rest. Find the greatest height of the 0.2 kilogram particle above the floor. So let's go back to our diagram and work out what they're trying to say. So both of these objects are starting 0.5 meters above the ground. Okay, as they fall, you can see that the 0.8 meter particle cannot go further than 0.5 meters. Okay, and because they are bound by this inextensible string, while they are moving together, the acceleration and their velocities will be the same, right? And so we can already say that the particle that is 0.8 kilograms will move down 0.5 meters, and as it moves down, the 0.2 particle must move up 0.5 meters. Okay, so it will start at 0.5 and it will move up another 0.5 meters. Okay, now once the 0.8 kilogram particle hits the ground, it will no longer be providing any tension. All right, it won't be pulling that 0.8 or the 0.2 kilogram particle up anymore, and so the 0.2 kilogram particle will continue moving upwards, independent of that particle, and it will move up an additional distance until it runs out of speed, because obviously it's going against gravity, and this is the distance that we're trying to find. Okay, so what we're going to do is we're going to try and calculate the speed the moment that the 0.8 kilogram particle touches the ground, and we can then work out what the small distance is after that. So, what do we know? Well, let's consider the 0.8 particle, okay? We know that it's going to have a displacement of 0.5 meters before it hits the ground. We know its initial velocity is 0. We calculate its acceleration as 6 meters per second, and it's positive because we're considering it moving downward in the direction of motion. So using v squared equals u squared plus 2as, we can solve for the final velocity of that particle just before it hits the ground. So v squared is equal to 0 plus 2 times 6 times 0.5, and so we'll get v squared equal to 6 meters per second. And I'm going to leave it like that because we're going to put it back into the equation. We can solve for v and say v is equal to square root 6 meters per second. If you, oh, sorry, not per second. That's not per second. This is like that. So that's the speed of the particle as it hits the ground. So as this particle hits the ground over here, it has a speed of, what did we work out? Square root 6 meters per second. Okay. Now, because these were joined together, that means that this particle at this very moment, the other particle touches the ground, must also have a speed of 6 or square root 6 meters per second. Okay. Now, the difference being going forward is going to be there's no more tension. Okay, so the only force acting on the object is its weight, and when the only force acting on an object is its weight and it has no resistance or anything acting apart from the weight, the acceleration is the same as the gravitational constant. So displacement is what we want. We know the initial velocity is square root 6. The acceleration is now going to be minus g because it's going against gravity, and because there's no other forces acting on it, it's just the gravitational constant, so this will be minus 10. We know that at the height of the maximum height of the particle, its speed will be 0, so its final velocity will be 0. So again, using v squared equals u squared plus 2as, we can just solve for displacement now. This is going to be 0 equal to 6 plus 2 times minus 10 times displacement. And so we get displacement equal to 6 divided by 20, which is 0.3 meters. Okay, and they want us to find the greatest height. So if we go back to our diagram again, we can see that that's its initial height plus the 0.5 meters that it was being pulled down by a particle of 0.8, and then finally that little bit extra that it continued when it was just using the remainder of its velocity. Okay, so we can say its greatest height is equal to 0.5 plus 0.5 plus 0.3, and that gives us 1.3 meters.